In this video, we're going to talk about the concept of arc length. Really, we should have called it curve length, but the name is what it is, and we're not going to be able to change it. So suppose I have a curve, and I'm trying to calculate the length of the curve from the point P on the curve over to a point Q on the curve. So what do I normally do? I'm going to go ahead and break up that curve into several smaller curves to get an approximation of the length. And how would I do that? Well, break up my x interval into n sub-intervals, and then at each endpoint I'm going to have a point P, and I'm going to connect those with just line segments, the secant line for the curve there. Calculate the length of each line segment and add that up, and that'll be my approximation for the length of the curve. Now each line segment, I would use the distance formula to calculate the approximate length of that portion of the curve. So delta SI will be the length of, the distance from the point P sub I minus 1 to P sub I, just the length of that line segment, and we'll use the distance formula for that. So our change in x, or delta x, is going to be constant, but the delta y is going to depend on I. So delta y1 may be bigger than delta y3, for example. And so we just go through, use the distance formula for each one, and get my approximation by adding those lengths of line segments together. Now here I'm going to do something interesting with this square root of the sum of the squares. I'm going to go ahead and factor out the delta x squared from the inside the radical. So when I do that, let me just take the time here to show what I mean. So I'm going to factor out delta x squared. I don't really need the sub I because I just said that it's the same thing. So inside the parentheses, I'd have 1 plus delta y sub I squared over delta x squared. So then if I break that into two radicals, the first radical will be radical of delta x squared, so that'll just give me a delta x, and then I'll have the radical of the second factor, which is what I did here. And now you'll see why. I'm going to let the number of line segments go to infinity. I'll wind up with an integral, the integral from a to b of radical 1 plus dy by dx squared dx. So let's go ahead and use this formula to calculate the length of the curve y squared equals x cubed from the point 0, 0 to 4, 8. So this blue curve is showing us what this particular curve looks like, and the shaded part, or the highlighted part, is the length that we're trying to calculate. So we're just looking at the upper branch, so I can just take the positive square root of both sides to get y equals x to the 3/2 power. So using the power rule, dy dx is 3/2 x to the power of 1/2. I'll need to square that. So let me rewrite that as 3/2 radical x, and square it to get 9/4 x. And so I need to find the antiderivative of radical 1 plus 9/4 x dx. I can do that with a u substitution. And go ahead and change my bounds. And then go ahead and calculate the antiderivative when I write the integral in terms of u, and perform the evaluation carefully. So I get 8 over 27, 10 radical 10 minus 1. Now, there's another way I could calculate arc length using a dy integral rather than a dx integral. Sometimes we have to use this alternate formulation. Sometimes it's just more convenient. So if we go back to our derivation, at this point, what I had done was factored out the delta x squared from the inside the radical sign. Well, I could just as easily factor out the delta y sub I, and then as n goes to infinity, I can go ahead and get this integral in terms of y. So let's use that formulation to calculate the length of the curve x equals y squared from the origin to the point 1, 1. Now, if I use my new formulation, I'll have a dy integral, which means everything has to be in terms of y, including the bounds. Well, in this case, both the x and y coordinate of each endpoint is the same, so there's no real focus needed to say, oh, it's got to be from 0 to 1. So dx dy is just 2y. And so now I'm left with calculating the antiderivative of radical 1 plus 4y squared dy. And there's no straightforward way of doing this. We could actually make a substitution where we would use one of the hyperbolic trig functions. But if I make a regular trig substitution, draw my triangle here, I can see that 2y would be equal to tangent theta, so dy is 1/2 secant squared d theta, and radical 1 plus 4y squared is secant theta. So if I write this integral in terms of theta, I'll get 1/2 integral secant cubed theta d theta. And you can see my strategy here is I'm not going to bother to change the bounds. I'm just going to find the antiderivative. Then I'll change my variable back to y and use the original bounds in terms of y. So we had previously calculated the antiderivative of secant cubed theta d theta. And I said at that time that we would be seeing it again. And sure enough, here we are. So let's review back to that slide from integration by parts. How do we find the antiderivative of secant cubed theta? We have to do integration by parts, use some trig identities, but in the end, the antiderivative is half, in brackets, secant tangent theta plus natural log of the absolute value of the sum secant theta plus tangent theta plus c. So I'll just use that as a formula and change that back to y. So tangent theta is 2y, secant theta is 1 plus 4y squared, the radical of that. So making that substitution, I can now evaluate that between 0 and 1 to find the arc length. And so I get 1/4 in brackets 2 radical 5 plus the natural log of radical 5 plus 2. So as you can see, with the arc length function or the arc length formula, we can sometimes get a very challenging antiderivative to calculate. And sometimes you can't find an antiderivative. And for some of the homework problems, you may even need to use one of our approximation techniques. If you can find the antiderivative, it's because the curve has a very special type of equation, and a lot of them are going to look like this. So I have x equals y to the fourth over 8 plus 1 over 4y squared, and I have my bounds on y. So since really everything is given as x as a function of y, I will use our formulation where we have a dy integral. And so I'll rewrite x in terms of powers of y, find dx dy, and now I have to do some algebra in order to calculate the integrand in a way where I can find the antiderivative. So I'll write them as two, or the difference of two fractions. Write that with a common denominator. To do that, I need to multiply the first fraction by y cubed over y cubed. So that gives me, as a single fraction, y to the power of 6 minus 1 over 2y cubed. Well, I need to square that and add 1. So when I square that, my denominator will be 4y to the power of 6. So let me write 1 as 4y to the power of 6 over 4y to the power of 6. I needed to use FOIL to get y to the power of 6 minus 1 quantity squared as y to the power of 12 minus 2y to the power of 6 plus 1. And now when I combine like terms, instead of having a minus 2y to the power of 6, I have a plus 2y to the power of 6. And the advantage of that is now I have a perfect square on the top and on the bottom. So both the numerator and the denominator are perfect squares, because in my integrand, I need to take the radical of 1 plus dx by dy squared. So when I take the radical, I'll just be able to take the square root of top and bottom. And I'll just have as my integrand y to the power of 6 plus 1 over 2y cubed. I can go ahead and break that up into two fractions, write those as powers of y. So when I take the integral, I just need the power rule to evaluate it. And so you may say to yourself, well, wait a minute, we did all that work, and the only difference between our integrand here and the original dx dy is this sign between. It's actually the conjugate of dx dy. And more than that, look, when you find the antiderivative, how does that compare to the original function? It's the conjugate of the original function. So that can be like a little sanity check for these problems. This you're going to see happening a lot. So then we just perform the evaluation to get 33 over 16. So let's see here. Here we've got another x in terms of y. And so we're going to go ahead and evaluate this, again, using a dy integral. So we're going to find the length of x equals the natural log of cosine of y from y equals 0 to y equals pi over 3. So let's go ahead and find the derivative. Derivative of natural log would be 1 over cosine of y. Then use the chain rule. Derivative of cosine of y should be negative sine y. So I've got a mistake here. Now, it didn't impact my final answer for getting that minus sign, because the next step I am going to square dx dy, and when I square it, the minus sign doesn't really matter. So now I don't really need to be concerned about absolute value signs, because I'm in the first quadrant and all of my trig functions are positive. So 1 plus tangent squared y is secant squared y. Radical secant squared y in the first quadrant is just secant of y. And the antiderivative of secant of y is natural log absolute value secant y plus tangent y. Just evaluate that between 0 and pi over 3. And I get my final value there. So one of the key takeaways is that the arc length integral can be written as either a dx or a dy integral. And we'll see later in the course that there's even more ways we can write this arc length integral.